Assalamu alaikum. Hello, everyone. I am Amine HOUSSAINI. I am a technical advisor, technical consultant in renewable energy and green hydrogen. So welcome to you all. Welcome to this exciting session where we will dive into the challenges and opportunities of green hydrogen infrastructure. And we will cover costs, we will cover also safety and some innovative storage solutions. So today we're very lucky to have great panelists who I will introduce quickly right now. So we have with us Mr. Ju-Yong Lee, who is manager at Korea Gas Safety Corporation, which is a Korean organization which ensures safety of gas throughout South Korea. Then we have Mr. Maarten van der Vlies. He is a renewable energy and green hydrogen expert. He's working at Rebel Group. Rebel is an advisory financial firm based in Netherlands and acting globally. Then we have Mr. Achraf. He's an experienced engineer with a focus on storage solutions. He's working at SOMAS. SOMAS stands for Société Marocaine de Stockage. And SOMAS is a key player in energy sector and specializing in storage of liquefied petroleum gas. So, as we've seen today over the sessions, green hydrogen is a chance and a great opportunity to decarbonize industries. However, we have still some challenges to overcome and to address. Some of these challenges are: how do we store safely green hydrogen? How do we make it financially attractive? How do we reduce the costs? And how do we make it both? How do we make green hydrogen infrastructure both reliable and efficient? So this is exactly what we're going to go through during this session. So we will look at some examples of safety standards with the South Korea example. We will see some great innovative storage solutions with an example in Morocco. And we will see how do we make cost challenges, let's say, how do we address cost challenges to make the scalable of green hydrogen a reality. So we have also with us Ms. Nouhaïla, who is a doctor at IRESEN, and at the end of this session, who will present us, let's say, a feasibility study of an example in the country. So I will give the floor to Mr. Ju-Yong Lee, who will take us to South Korea and see how this company is ensuring safety of hydrogen in the vehicle and refueling stations example.
Thank you. Hello, everyone. My name is Ju-Yong Lee, and I am a senior manager at Korea Gas Safety Corporation. Currently, I work in the International Relations Department, but I have spent most of my career testing and certifying hydrogen vehicle components. In fact, every hydrogen vehicle in Korea has passed through my hand. Korea is the leading country in the world for hydrogen vehicle, and the industry here is incredibly active. I can easily see hydrogen vehicle on the road in my country thanks to our advanced infrastructure and supportive government policies. Today, I would like to share some insights into the hydrogen vehicle industry and the certification system in Korea, which is the most active in the world. I hope this will be a brief yet informative session for those considering the hydrogen vehicle industry in collaboration with Korea in the future. Thank you for your attention. Let's dive in. First, I will introduce the Korea Gas Safety Corporation, which I work for. KGS is established in 1974. It is the only agency which controls gas safety, such as fuel gas, high pressure gas, including hydrogen in Korea. KGS under the control of Ministry of Trade, Industry and Energy. You can think of KGS as handling everything related to gas in Korea. Korean government designates 3 dedicated hydrogen agencies. One is Hydrogen Promotion Agency as H Korea. The other is Hydrogen Distribution Agency is KOKAS. The last is Hydrogen Safety Agency as KGS. KGS is Hydrogen Safety Agency by Korean government. As you can see from our work, KGS work a core role in the hydrogen industry. I will explain the outline of Korea hydrogen vehicle industry. As you can see from the sales of domestic hydrogen cars is gradually increasing. In 2023, a total of around 34,000 hydrogen vehicles were registered in South Korea, continuing impressive growth since 2015. Together with electric and hydrogen vehicles, the share of environmentally friendly vehicles among the total number of registered vehicles in South Korea was about 8% that year. In the case of hydrogen buses, it started with 77 units in 2020, and by June 2024, the number has increased to 989, surpassing 1,000 units currently. Thanks to these efforts, hydrogen buses and cars are easily found while driving Korea. From now on, I will explain Korea's hydrogen vehicle components certification system. In the case of components that enter hydrogen vehicles, all components that have a pressure of more than 3 megapascal are to be tested by KGS. During the test is conducted with a pressure of more than 70 to 90 megapascal. For hydrogen vehicles, valves, and safety devices, both design stage inspections and production stage inspections are required. Before production, prototype products undergo design stage inspections, and after passing these inspections, each subsequent production must be inspected by KGS. For products other than valves and safety devices, testing is only required during the initial product development. The quality is then verified through annual factory inspections. KS certification might be unfamiliar to you as it is a certification system unique to Korea. It is only applied to 3 components of hydrogen refueling stations. To maintain KS certification, both product testing and factory audit are required. There are few certification systems for hydrogen refueling stations components worldwide, so many international manufacturers of these components seek to obtain Korea's KS certification. Although the test method is slightly different for each component, the overall process is as follows. First, the corrosion test is conducted, and then the component is subjected to a pressure of 70 megapascal, approximately 50,000 times, to verify its durability. After that, the component is pressurized with water about 150,000 times. Finally, the internal and external leakage test is checked at around 90 megapascal. If the component pass all these tests, it is considered successful. Assuming there are no failures during the test, the entire process takes about 3 months. During this inspection, we also conduct factory audit. Through this audit, we comprehensively check the quality system of the factory. For KS certification and KGS performance certification, we perform annual factory audit to ensure that the factory maintains its quality system. The factory audit are conducted to a standard equivalent to ISO 9001. The last thing I will explain is the future of the Korean hydrogen vehicle industry. 271 hydrogen refueling stations have been established across the country now. And the Korean government plans to increase the number of 1,200 by 2040 to increase infrastructure and improve service so that they do not feel uncomfortable refueling even with the expansion of hydrogen vehicle. In addition, hydrogen vehicles also aim to produce 6 million fuel cell electric vehicles by 2040. For this reason, the number of companies that want to sell hydrogen vehicle components or refueling station components to Korea is increasing worldwide. So far, thank you for listening to the explanation of the Korean hydrogen vehicle industry and certification system. Thank you.
Thank you very much, Mr. Lee. So South Korea is very advanced in hydrogen in vehicles. So let's move now to Mr. Van der Vlies.
Thank you, Amine. Yeah, so, and thank you also to everyone who's still here. It's already quite late, so thank you for that. I'm a numbers guy, I'm a financial advisor, and when I was asked to speak, I thought, okay, I can speak about bankability issues, I can speak about financial viability stuff, but probably that has already been addressed multiple times today, which was indeed the case. So I decided to share a few insights on levelized cost of hydrogen, which is a number that you hear a lot. We do not always call it levelized cost of hydrogen, but whenever people say we produce hydrogen for $2 or we expect it to go down to 1.5, those are the numbers that are typically referred to as levelized cost of hydrogen. And there are a few things you need to know about levelized cost of hydrogen in order to understand what it means. So won't spend too much time on the definition of levelized cost of hydrogen. It's a bit technical, but basically what you want to do when you look at the levelized cost of hydrogen is you want to assess how much does it cost to actually produce the cost of a molecule of green hydrogen. That does include all the costs, and it also includes a profit. So you do expect it to include a profit for the financial sector, banks that finance it, and obviously private investors that put their money into these projects. So levelized cost of hydrogen includes that portion of the profit. And that means you can actually compare it to what the market is willing to pay. So it's a simple image. You either have a deal if the levelized cost of hydrogen is lower than what the market is willing to pay, and you have no deal if it's the other way around. Now, there are a few things that are important to know. Three main characteristics of levelized cost of hydrogen that influence your interpretation of that number. And those three are levelized cost of hydrogen is very sensitive to time. Levelized cost of hydrogen can be calculated at different stages in the hydrogen value chain. And levelized cost of hydrogen is very dependent on the cost of capital that you use to calculate that number. I'll show three quick examples. So this is an example of a levelized cost of hydrogen for a green hydrogen project here in Morocco. We did at Rebel build a levelized cost of hydrogen simulator where we can actually assess the cost of producing green hydrogen in different parts of the world based on available hourly data for solar and wind energy. And I've done that for Morocco 3 different times in the future, 2030, 2040, 2050. And you'll see the costs go down. And obviously, this is not a surprise. We've all talked about it. We do expect costs for green hydrogen to go down due to economies of scale, technology developing, efficiencies becoming better. And you'll see that illustrated in this graph. Now, I am not sure these are the actual right numbers because they do depend on assumptions, and they do also depend on quite aggressive assumptions on how costs will go down, and whether that actually will be realized. It might be a bit too optimistic what you see here in the graph, but it is important to know when someone tells you I can produce green hydrogen for 1.5 euros or dollars a kilo, that you know what time are we talking about. That's the point I tried to make. The second thing, it's about the stage of the green hydrogen value chain. So what we do see a lot of the number I just showed you on the screen on the previous slide is about how much does it cost to produce green hydrogen here in Morocco on the site. What we sometimes forget to add to the number are all the costs related to storage, all the costs related to transporting that molecule to wherever it's needed. And especially when we're looking at export projects, that means with the technology of today, we need to go through, for example, ammonia, it's the example on the slide. We need to go through that conversion process. We need to ship all that ammonia to the import location. And that means a whole bunch of costs and inefficiencies get added to the levelized cost of hydrogen. And so if you look at the levelized cost of hydrogen at the offtake location, you'll see it here in the slide, you get to a completely different number because it does include all these additional costs and all these additional inefficiencies. And so it's important also to realize that when we talk about levelized cost of hydrogen, we often talk about the image on the left side of the screen, and we sometimes forget to add all the costs that do get added to it that are on the right side of the graph. And finally, what I wanted to say is, and also obviously this is not unknown to you, levelized cost of hydrogen, so the cost of producing hydrogen is very dependent on the cost of capital, so the financing costs for a project. That includes interest from banks, it includes return requirements from investors, and the cost of capital that you use for your levelized cost of hydrogen calculation influences the outcome. So I just went back to my 2030 scenario where we only look at production costs and we don't look at supply costs. And you'll see the influence of just the cost of capital on the levelized cost of hydrogen. So I ran a few scenarios where we use, for example, Germany's cost of capital, the cost of capital for a project in Germany, which would be the Germany weighted average cost of capital. And I ran a scenario with Morocco's cost of capital, which is higher, considering a lot of different factors. And you'll see the impact of that. And this is a small example, but when we also look at other examples in the world, you can potentially see much bigger differences. That's where I want to end. Just a few insights on the levelized cost of hydrogen with the message, make sure that you know what is in the number and what is not in the number.
Thank you very much, Maarten. There is a lot of hope. I think the numbers and the figures you've showed give all of us a lot of hope. There must be complex models behind, let's say, to do some forecast, but there are still forecasts. But thank you very much, Maarten. Let's move now to Mr. Achraf ESSALIH, who will talk about SOMAS and how SOMAS is storing gas today and how this can be applied to green hydrogen.
Thank you so much, Chairman, and dear speakers, distinguished speakers, and dear audience. I'm honored to be amongst you today. I have the hard task to disseminate a 4-year project into 10-minute speech while avoiding making you sleep, so wish me good luck. Today we are talking about the Milhi project. It's a project that aims to demonstrate the technical, environmental, and economical feasibility of underground storage of hydrogen in salt caverns. The study was financed by IRESEN and with a consortium of Green Energy Park, SOMAS and HDF as industrial partner, ONIM, and for R&D, the University of Ibn Tufayl. But first of all, what is SOMAS? SOMAS stands for Société Marocaine de Stockage, which just blowed the 50th candle of birthday last July. It is a pivotal actor in underground storage solution in salt caverns for 50 years for the storage of the LPG for now. We are ensuring the strategic storage of LPG for the national consumption of this substance. However, we are readying ourselves to adapt and to make available our expertise and underground salt caverns for the upcoming and much and highly anticipated energy transition. So, what is the salt caverns? In a nutshell, we are using a salt layer deep underground, about 500 meters under the ground, and we are creating a volume in which, or a capacity in which we are storing energy products, such as LPG for our case, but in worldwide there is a lot of uses for crude oil, for other products also, and also it could be used for hydrogen. The process of creating such capacity is called leaching. In a nutshell, we inject water that dissolves the salts, and by this process it creates the capacity and the volume needed. So to give you a brief overview of the project Melhi. By the way, Melhi stands for in Arabic milh, or salt. It's in Arabic, and the HY is for hydrogen. We needed to respond to questions. First, why the site selection? Why we are choosing SOMAS? First, we are leveraging 50 years of operational data and the knowledge of the underground of this area. Second, the strategic positioning of SOMAS near the sea and near the major petroleum port. Why we need the sea? Because the leaching uses a lot of quantities of waters. It's in the range of million cubic meters, so it's out of the question the water of everyday use. So we use seawater. Also, we need to be close to the port for the importation or exportation of the substance we are storing, and also for the case of Power to X, we need to be around potential off-takers. The hydrogen could be used as a mean to fight the intermittence problem for renewable energy. Could be used for, as we say in other session, for the e-fuel, and also it could be used for the green ammonia. And that's for the site selection. The regulatory framework that we used in this project is the law of mining code, the 33.13. It just occurred in the last years, and it introduced some requirements for the creation of salt caverns, such as the permitting and license. The third question is about the risk and environmental assessment. I will not go into the details, but I chose the major risks and environmental impact. For the environment, the major environmental impact is the water use. As I said earlier, it's in the million cubic meters range. So that's why we use the seawater for the leaching. And after that, there is the rejects of that brine. We conducted some studies and hydrodynamic studies in a reject point in the sea, and we proven that the salinity is not above 0.6% of the salinity of the sea in around 300 meters. So the effect in that area with the currents of the sea is very limited. For the major risk, that was identified is the hydrogen reaction or embrittlement with the material. We find that the material that we choose for the surface installation, like pipelines and valves, is a crucial and essential part of the risk assessment, because, as you know, the hydrogen is the smallest atom in the periodic table, and it has the capacity to sneak between the crystalline structure of metallic material or alloy, and it causes weaknesses and can induce micro leakage that is uncontrollable. So for the technico-economic prefeasibility, first we have the inputs. We chose a cavern that has the same characteristic as the cavern that we use. So it is a 200,000 cubic meters of capacity in the same depth as around 500 meters underground. And we chose to have a rapid cycle. When we say rapid cycle, it means we fill and discharge the cavern in a very high frequency. So the output of this study, we have the pressure differential, or the highest pressure that we can have in those type of cavern is around 71 bars, and the lowest is 29. So what it means that we will have a cushion volume. A cushion volume it's a volume of hydrogen that we invest in the first filling that we will never use. It will stay in the cavern. It is around 46% of the volume of the cavern. The working gas is the gas that we will add to that cushion gas, and until we have the highest pressure, which is about 550 tons of hydrogen. So it's about 54% of the total capacity of the cavern. With the performance that we can have, we have some safety constraints about the rates of injection of hydrogen. The pressure differential should not exceed 10 bars per day. So the material cannot be weakened by the high pressure differential. By that, we have an average rate of 138 metric tons of hydrogen that could be cycled per day. So to sum up, for 1 year, we can cycle in one cavern, about 25,000 metric tons of hydrogen. After that, we needed a development scenario. We took a reference, at the time, the national roadmap for hydrogen, and we chose the reference case for 2013. And we developed a scenario to how much we develop the storage to augment it and to follow the need or the need of the market. And I will go directly to the last slide. As you see in the graph, it is, by the way, a logarithmic scale, because there is a big differential. If we did not the logarithmic, we will draw it in the ceiling. So there is, in 2030, we will be at 75,000 metric tons in comparison to 220,000 metric tons for the reference case in 2030. And in 2040, we will be at 275,000 tons in comparison to the reference case, which is 880,000 tons. So in conclusion, the strategy was intended to be ambitious, but we know that not all the hydrogen production will be stored in the cavern. So we make the development to retain up to 10% of the hydrogen production, which represent 10 to 25% of the reference case on 2014. And the modularity of this scenario could make us accelerate or decelerate following the market development. So it's just, we did a planning, but it could be accelerated or decelerated. So the next step for the project, we need to be focus more on a precise scenario in order to estimate more the storage requirement for the hydrogen needs. Thank you so much.
Thank you very much. Thank you very much, Achraf. This is a very promising technology to store green hydrogen. Yeah, I think it's proven, it's ready, but obviously it comes with, let's say, some investment costs and also with some risks, but that are definitely manageable. So I'll have some questions to ask. So I will ask my first question to Mr. Lee. So once again, Mr. Lee, thank you for your presentation. So you took us to the certification process of green hydrogen vehicles in South Korea. We all know that obviously the number of cars is going to increase over the coming years. So what is your organization doing to ensure safety with the expanding of these cars?
In Korea, as the number of hydrogen vehicles increase, we are making great effort to expand the safety measure. First of all, we are planning to change the test standards for hydrogen vehicle components this year. The reliability of the existing test standards was slightly lowered because it allowed for testing with nitrogen or helium instead of hydrogen. However, we are trying to change the national standards to the ECER 134 test standard, which is tested using hydrogen. And for valve used in hydrogen refueling stations, 3 products are currently subject to KS certification, and we plan to add 3 more components, expanding the certification target to 6.
Okay, thank you very much. Thank you very much, Mr. Lee. I have actually 2 questions for you, Maarten. I mean, your presentation was excellent. Thank you for that. And you, let's say, presented us some insight about the costs, which are actually attractive. But I want to ask you, I mean, in the geopolitical context that we know with the changing environment, when we do and when your firm is doing some forecasts and I mean costs in 2030 or 2030 are still predictions. So how, I mean, can you give some comfort to decision makers and to banks in reference to these forecasts that you're doing and give them confidence that the estimations are accurate? And this is the first question. And then also, if you can tell us about, I mean, you give some forecast because, but then obviously we will, I mean, everyone will try to reduce these costs. So can you give us just maybe some paths to go through, let's say, to reduce these costs? Thank you.
All right. The first question is not so easy to answer, but it's a good question. Obviously, we are not a research institute, so we are actually we are not behind the forecasts for electrolyzer costs. We are not behind the forecast for wind turbine and solar PV technology costs. We use the references and the studies that are done, for example, by IRENA and the World Bank. We use those kind of numbers in our models. So that's where we refer to when we talk to other parties and banks. But at the same time, we do a lot of work directly for the industry and for the private sector. And in those conversations, and obviously this, what I just showed on the screen is a very high-level generic model. You start to really, develop a model for one particular project, and then the information comes directly from OEMs. It comes directly from the private sector that is developing that project. So I cannot answer the full extent of the question just because we are not behind those numbers ourselves. But what I can say from the discussions I've had with parties that are directly involved in the sector, the numbers from the studies that we're using for this model are already a bit too optimistic. So the decline that the world was expecting is not yet there. And that's directly in bridge to the answer to the next question. One way to bring these costs down is by actually deploying these technologies on scale. That was also said in one of the previous sessions. Deploying it on scale and actually realizing those economies of scale, the technology efficiency and the cost will go down. So that's on the CapEx, on the investment side. And obviously the other component are the financing costs. So you saw it, I mean, it's a bit of a metric in a calculation, but the cost of capital actually plays a significant impact on the cost of hydrogen. So if you are able to reduce that cost of financing by working together as financial institutions, as governments, together with the private sector, it should be possible to do that.
Okay, thank you very much, Maarten. I think we got your point. Achraf, once again, thank you very much, let's say, for presenting us SOMAS and, let's say, this technology of storage. I think next to you we have Nouhaïla, who has also worked with you on this feasibility study on Malhi. So Nouhaïla, can you tell us more about your work and let's say the takeaways of your feasibility study on Malhi project?
Thank you, Amine. So I would like also to thank my colleague Achraf for disseminating the relevant results of the projects. So my role is coordinating the project. It was very enriching experience for me to coordinate this new emerging also topic, which is the hydrogen, studying the hydrogen storage in salt caverns. So the project have tackled three main aspects. First one is about relating also the state of the art of the technology. And also we have focused on the environmental and risk management and impacts of the project. And last but not least, we have also tackled with the support of our subcontractor Geostock the technical feasibility of storing hydrogen in salt cavern. So I'm here just to share some few words about this enriching experience. It was really good to work in close with the partners from different angles. So SOMAS, I have here with me Mr. Achraf, and from also Hydrogène de France, Hanan Ahmarawi. Unfortunately, she's not here with us because she has a flight. And also from the University of Qinitra, Ibn Tufail, we have Professor Abdelaziz Meredakh and also his PhD student, Ibtihal Aishouni. Unfortunately, they are also not able, they haven't been able to participate today. So on the light of the closing or closure of this project, I would like to address my warmest thanks to all partners and for their engagement and serious engagement, and also for the team of the funding agency of IRESEN, especially Mrs. Sokaina Boudouh, our evaluator, and also my colleague or from the team of the financial or the funding agency, Mrs. Asma El-Khalifi. She's not here with us. I would like also to address thanks to her. So this is my few messages that I want to say. And also I would like to call Carolina. She is representing Hydrogène de France for a photo of the group of the dissemination. So I hope you have some insightful results about the project, and thank you.
Thank you very much. I just maybe see in the audience if there is any questions. So if there are no questions, please accompany me with some applauses for our panelists today. Thank you very much. And yeah, so we close this session. Thank you very much for your attendance.